some of what we know about rate laws at this point. We know that we can define a rate as being essentially a change in concentration of a substance over a time interval. Now, to make sure we get the same rate no matter which substance we measure, we divide by its stoichiometric coefficient, and if it's a reactant where the concentration is decreasing, we throw in a minus sign. Something that's inconvenient about this is we have to take at least 2 concentration measurements at 2 different times to use this definition and find our rate. A little bit more powerful, we also have rate laws, and it just happens that some reactions can be written such that their rate is equal to a constant times the concentration of the reactants raised to powers. Doesn't work for every reaction, but some of them can be expressed this way. The nice thing about this is we can take a single concentration measurement and we immediately know the rate, and it's the exact rate. It's not the rate over some interval. But unfortunately, if we wanted to know the rate at any other point in the reaction, we'd have to still measure the concentration again. Now, this gives us a nice mathematical relationship, which seems to govern the reaction. So it might make sense to us that we should be able to figure out a way to express these concentrations, or even these rates, at any given time by modeling the reaction. So our solution is the integrated rate laws. They're going to relate concentration and time, and they'll require only one concentration measurement, which we can perform at any time during a reaction. And if we do it once and we have our rate equation, then we can figure out what the concentration is at any other time. And the reason these are called integrated rate laws is because of the way that they are derived. This is going to borrow some calculus, which it's okay if you're not familiar with. You aren't going to be expected to perform these derivations. But I thought I would go ahead and show you anyway where this comes from. So if we have a 0th order reaction, this is where our exponent on the concentration is 0. And so it's just going to become equal to 1. So our rate is just going to become equal to k. For this reaction, our rate definition would be 1 over 1 negative times the change in concentration over the change in time is equal to k, which we can express like this. Our main problem is these deltas. If we didn't have these deltas, then we would have a direct relationship between concentration and time. Well, there's a trick from calculus to get rid of these deltas. It's called integration. These deltas, they refer to an interval. And integration is also going to be performed over an interval. We're going to perform it from some starting time to some finishing time. And to go along with that, we're going to split this into pieces. So we'll integrate our delta t from the starting time to the final time, and then our delta concentration from the initial concentration at this starting time to the final concentration at that final time. And when we do that, it converts our delta into exact quantities. And what happens is we get the difference in the final concentration minus the initial concentration is equal to minus the rate constant times the final time minus the initial time, which the initial time we're just always going to take to be 0. So this is just minus kt. And we can rewrite this as so. So if we want to find the final concentration at any time, as long as we know the rate constant and the time and the initial concentration that we're starting with, we can go ahead and calculate that. And if we knew some of the other ones, we could go back and calculate any missing parameter. So this is what's called an integrated rate law, and this has been the derivation of the 0th order integrated rate law. So for 0th order reactions, we can use this equation to figure out our concentration at any time. Well, these are the results for a 0th order, 1st order, and 2nd order reactions. So reactions where the rate is just equal to k, where the rate is equal to k times concentration, or the rate is equal to k times concentration squared. So we already saw for the 0th order reaction. These are the equations for the first and the second order reactions. I've also given you the formulas for the half-lives for these. And what the half-life is how long it takes for exactly half of your starting substance to be consumed. Well, let's say that we have a 0th order reaction. An example of such a reaction would be where hydrogen iodide decomposes to make hydrogen gas and iodine gas. The rate constant for this reaction is 0.05 molars per second. How long does it take to reduce our starting concentration of 3 molar down to 1 millimolar? Well, we can definitely use our integrated rate laws for this because our question involves the relationship between concentrations and time. So this is our integrated rate law for the 0th order reaction. And what remains is simply to plug in these pieces of data and solve for t. So go ahead and start doing that. So here is my final concentration. Here is my initial concentration. And then here is my rate constant. I need to solve for t. So I'll go ahead and subtract this 3 molar from both sides and divide by this negative 0.050 molars per second. And that gets t by itself. And the answer comes out to 60 seconds. And you can note here that the units work out. We have molars up top and molars in the bottom, so that cancels out. And then we divide by seconds twice, which flips it back up into the numerator. Let's say that we had a first order reaction now. Hydrogen peroxide decomposing to give us water and oxygen. The rate constant here will be 1.15 times 10 to the 3 inverse seconds. Note that we have different units since this is now a first order reaction. What will be the concentration after a millisecond if we start at 2.7 molars? Well, since this is a question about concentrations and times, we can use an integrated rate law. This time we'll use the integrated rate law for a first order reaction. Now plugging in our values for K, our rate constant, and our elapsed time was 0.001 seconds, 1 millisecond. And then our initial concentration for A naught here, 2.7 molar. We get a value of negative 0.157. Now, a couple of cautions here. One caution is that your calculator might call this natural log just log, L-O-G. So make certain that you don't get confused between the log base 10 and the log based e. They're different. If you type log 10 into your calculator and it gives you 1 as your answer, you're using the wrong log. The other caution here is sig figs. We have a different rule for logarithms. And our rule for logarithms is that you go by the number of sig figs here. It's going to be the number of decimal places you carry out your answer to. And so here we had 2 sig figs, so I will go 2 decimal places over in my answer. And I will add this 0.99 to my result here to give me this result, the minus 0.157. Now the inverse function of a logarithm is an exponent. Here this was log base e, so to undo this function, we're going to take e to the power of whatever that quantity is. And because we did that to the left side, we'll also have to do that to the right side. Take e to the power of minus 0.157. And you should have an e button in your calculator that you can use to do this. And if we do that, that gets rid of all of this junk here and just leaves us with the concentration at the particular time. And on the right side, we get answer of 0.85. And here we have to kind of tack the units back on. We know this should be in units of molarity. The integrated rate laws that you've been given have all been written in a special way. They've been written as linear equations. That means when you plot them, they should come out as a straight line. So our general line equation is y equals mx plus b. For all of our integrated rate laws, there's an exact correspondence. We just call y something different, and we call x something different. But whatever we choose for our dependent variable here, whatever multiplies it, that is going to be the slope of our plot. And so if we plot our data and we measure the slope, then we will know the rate constant, or the negative rate constant. Likewise, whatever we're adding, that's going to be our intercept. And so if we know where the line intercepts for a zeroth order reaction, then we know that that's the initial concentration. If we know where the line intercepts the y-axis for a first order equation, we know that that's the natural log of the initial concentration. And so we can exponentiate it like we did in the previous example to get this into our initial concentration. So we'll have to be careful here to make sure that this works. We'll have to plot the right thing. So here, x corresponds to time. So we'll go ahead and plot time as our x variable. And then in these equations, what stands for y is different. So in the first equation, it's the concentration, but in the second equation, we'll have to take the natural log of the concentration. And the third equation, we'll have to take the reciprocal. Now, something we can do is we can go ahead and try this for whatever data we have. And if we've guessed the correct rate law, then we will get a nice linear fit. And if we've guessed incorrectly, then our data is going to curve off in some direction. So an example of that, we have the reaction where some N2O5 decomposes itself to give us nitrogen dioxide and oxygen gas. And so we do this in the laboratory, and we have a sensor for this N2O5 maybe. And so we measure its concentration and molarity with respect to time. From this data, what should be the rate equation for this reaction? Is it zeroth order? Is it first order? Is it second order? And what's the rate constant to go along with that? Our strategy is that we're going to go ahead and try to plot this, assuming that it's a zeroth order reaction, and that it's a first order reaction, and that it's a second order reaction, and we'll see which one works. Now, of course, if you're doing this yourself and you find one fits, you can stop there. You don't have to try out the other ones. Well, in order to plot all these different order types, we're going to need to convert our data, because the first order reaction involves a natural log of the concentration. So what we said corresponded to y. And the second order reaction involves taking the reciprocal of the concentration. So we'll go ahead and convert our concentration data so that we have the y's for all those different reaction types. Now we'll go ahead and try plotting it. And when you plot it, you can do a linear regression on your calculator. And this will give you a line equation, which will tell you what the slope is and what the intercept should be. You can also use Excel or Wolfram Alpha or a lot of other tools in order to do these linear regressions. You might want to look up the data on whatever tool you're going to be using. And so we try this using, first of all, for the zeroth order, we use our time data and our concentration data. For the first order, we use our time data and our natural log of concentration data. And then for our second order, we use our time data and our reciprocal of concentration data. And we try plotting all of those and see if we get any straight lines. And here, I've done the linear regression for all of those. And so the computer has tried to figure out what would be the best straight line fit for these. You can see for the zeroth order, it kind of curves away from the line a little bit. For the second order, it also curves away from the line a little bit. But for the first order, all of these points land directly on the line. Now, sometimes you'll have noisy data. So you'll have these a little bit, randomly above or below the line. but it will still be a nice straight fit. And it won't be that you have this trend where all the data points kind of curve like they do in these ones. So this means that we have a good rate law using the first order equation. And so the rate law for that is constant times the concentration of the reactant to the first power. Now we can correlate the coefficients from our equation the calculator spat out to our integrated rate law equation in order to figure out what this k should be. Because these are equations for the same line, and so everything has to match up. So this is the y, and this is my x. This is my slope, my m, and the m here has to match the m here. So we have that minus 1.695 times 10 to the minus 3 is equal to negative k, which means that k is going to be equal to positive 1.695 times 10 to the minus 3. And we have to sneak our units back in because our calculator doesn't know about units. But we know that it's going to have to be inverse seconds here, either by looking at this equation and knowing that we're going to have molarity divided by seconds as our rate. And so this, we have to have inverse seconds for k. Or we might look here, and this doesn't have dimensions, which means this needs to not have dimensions. And since this is time, this is going to have to be inverse time to get rid of those units. Now we have all the pieces to go ahead and write our full equation, which we said was a first order equation. So the rate is going to be proportional to the concentration to the first power, and then we solve for k. So this is our full rate equation for this reaction.